channel Easy Chem Master. Ours today topic is paracyclic reactions. Paracyclic reactions are a special class of organic reactions that proceeds through a concerted recognized of electrons. Concerted, all bond breaking and bond making happen in a single step. No intermediates, the reaction does not pass through carbocation, radicals, or carbanions. Instead, it goes directly from reactants to product. Single cyclic transition state. The electrons move around in a closed loop. Now we can see the types of paracyclic reactions. Paracyclic reactions are classified into 5 types. Those are 1. Electrocyclic reactions, 2. Cycloaddition reactions, 3. Sigmatropic rearrangements, 4. Cheletropic reactions, 5. Group transfer reactions. In this video, we can learn each of the above in detail. The paracyclic reactions are explained by 3 main theoretical approaches in organic chemistry. It highlights that all the 3 theories are valid and correct, but they differ in approach and ease of use. The 3 theories are 1. Woodward-Hafmann theory. Based on the conservation of orbital symmetry. It was the first theory developed historically, in 1965. Relies on correlation diagrams to track how molecular orbitals change during a reaction. 2. Fukuy's Frontier Molecular Orbital Theory, FMOT, focuses on HOMO, highest occupied molecular orbital, LUMO, lowest unoccupied molecular orbital, orbital interactions, usually considered simpler and more intuitive than Woodward-Hafmann. It helps to predict reaction feasibility by looking at orbital overlaps. 3. Dewar-Zimmermann theory. It explains paracyclic reactions using the concept of an aromatic transition state. If the transition state is aromatic, the reaction is allowed. If anti-aromatic, it is forbidden. Easiest to apply across all reaction types, but less intuitive for understanding the underlying orbital reasons. There are 3 factors that determine the outcome of paracyclic reactions, like electrocyclic, cycloaddition, sigmatropic rearrangements. Those are 1. Number of electrons involved. Paracyclic reactions follow the 4n and 4n plus 2 rule. Whether a reaction is allowed, symmetry allowed, or forbidden, depends on how many pi electrons are involved. Example, 4n electrons, e.g. 4, 8, 12, behave differently from 4n plus 2 electrons, 6, 10, 14. 2. Stereospecificity. The reactions are highly stereospecific. The stereochemistry of starting materials dictates the stereochemistry of products. Cis gives cis and trans gives trans, depending on the orbital symmetry rules. This is why predicting stereochemical outcomes is a central part of paracyclic reactions. 3. Conditions. Heat delta versus light, HRV. Thermal conditions, delta. Reactions proceed via the ground state electron configuration. Photochemical condition, HV. Excitations of electrons to higher orbitals changes the symmetry, often reversing the allowed or forbidden reactions. Example, a reaction forbidden under heat may become allowed under light, vice versa. Now let's start the electrocyclic reactions, which are a major class of paracyclic reactions. Electrocyclic reactions. These are reactions involving ring opening or ring closure. They involve the conversion of a pi bond into a sigma bond or vice versa. They are classified by the number of electrons involved in the conjugated system, usually 4n or 4n plus 2 pi electrons. Examples shown in the image. 1. Butadiene to cyclobutene, a 4 pi electron system. The open chain conjugated DNA, butadiene, can close to form cyclobutene, or the ring can open back to the DNA. 2. Hexatriene to cyclohexadiene, a 6 pi electron system. A conjugated triene, hexatriene, can cyclize to form a cyclic DNA, or the ring can open to regenerate the triene. 3. Allylic cation to cyclopropyl cation, a 2 pi electron system. The allyl cation can ring close to form the cyclopropyl cation, or the reverse ring opening can occur. This slide explains diastereoselective rules in electrocyclic reactions and how they depend upon the number of pi electrons, 4n or 4n plus 2, and their reaction conditions, heat and light. It uses 4 cases to show stereochemical outcomes. Stereochemistry depends on whether the reaction proceeds by conrotatory substituents rotate in the same direction, or disrotatory substituents rotate in opposite direction, motion. Case 1. 4 pi electrons under heat delta. Example, butadiene to cyclobutene. Thermal reactions of a 4 pi electron system proceeds conrotatory. This determines whether substituents, R groups H, end up cis or trans in the product. Case 2. 4 pi electrons under light, HV. Photochemical reaction of a 4-electron system proceeds disrotatory. Stereochemical outcome is reserved compared to the thermal case. Case 3. 6 pi electrons under heat, delta. Example, hexatrine to cyclohexadiene. Thermal reaction of 6-electron system proceeds disrotatory, leads to specific stereoisomers depending on substituent orientation. Case 4. 6 pi electrons under light, HV. Photochemical reaction of a 6-electron system proceeds conrotatory. Again, stereochemistry is opposite of the thermal pathway. Summary rule: 0.4 e to n electrons, 4.8. Point: thermal is conrotatory, photochemical is distrotatory, 4n plus 2 electrons. Thermal is distrotatory, photochemical is conrotatory. This slide summarizes the Woodward-Hoffmann rules for electrocyclic reaction proceeds conrotatory or disrotatory, depending on the number of pi electrons and whether the reactions is under thermal delta or photochemical HV conditions. Table explanation: the number of electrons equals 4n, 4, 8, 12, and so on. Thermal, delta. Conrotatory number of electrons equals 4n plus 2, for example 6, 10, 14, and so on. Thermal, delta. Conrotatory, where n equals integer, mnemonic in the slide. 6 points for a touchdown is 6e dash. Thermal, disrotatory. This is a memory trick. A 6 pi electron system, like hexatrine A is cyclohexadiene, under thermal conditions reacts in a distrotary manner. But why? The why comes from orbital symmetry conservation, the Woodward-Hoffmann principle. Depending on electron count, the frontier molecular orbitals, HUMO/LUMO, have different symmetry properties. To maintain bonding overlap during the reactions, substituents must rotate in a specific way. 4n systems, thermal equals conrotatory, photochemical equals disrotatory, 4n plus 2. System, thermal equals disrotatory, photochemical equals conrotatory. This slide explains theory number 1. Woodward-Hoffmann correlation diagrams, which is one of the key ways to rationalize. What are correlation diagrams? A method to track the symmetry of molecular orbitals, MOs, from reactants to transition states products. They show how orbitals transform as the reaction progresses. Main points from the slide. 1. Consider all molecular orbitals, MOS, involved, not just HOMO and LUMO, but the entire set of occupied and unoccupied orbitals. 2. Consider symmetry of MOS in starting material product and transition state. The key idea is that symmetry must be conserved through the reaction. If the symmetry is preserved, the reaction is allowed. 3 orbitals of different symmetry can cross. Orthogonal orbitals, different symmetry labels, do not interact, so crossing is allowed without issues. 4 orbitals of same symmetry cannot cross. If 2 orbitals of same symmetry try to cross, it would lead to very high energetic cost, not allowed. This restriction explains why some reactions are forbidden. 5. We care about where the electrons end up. The focus is on the orbitals that end up occupied in the product, since these determine bonding and stability. Why it matters? Correlation diagrams provide the theoretical justification behind the Woodward-Hoffmann rules. Great, this image is showing an example of a Woodward-Hoffmann WH correlation diagram applied to an electrolyte reaction ring. Opening, which closing of butadiene is cyclobutene. 1. Reaction type cyclobutene. A 4-pi system in the closed ring can undergo electrocyclic ring opening to give butadiene. Conversely, butadiene can undergo ring closure to cyclobutene. Two possible pathways. Disrotatory transition, state TS. The terminal p orbital rotate in opposite directions. Conrotatory transition, state TS. The terminal p orbital rotate in the same direction. These motions determine whether the symmetry of the orbitals is conserved or not. 3. Correlation diagram, the vertical stacks of orbitals. On the left side, MOS of cyclobutene, the closed ring form. On the right side, MOS of butadiene, the open chain form. The lines drawn show how orbital of similar symmetry are correlated during the reaction. Outcome for a 4-pi like butadiene is cyclobutene. Thermal conditions is conrotatory pathways allowed. Photochemical conditions is disrotatory path is allowed. Perfect. This is a detailed Woodward-Hoffmann correlation diagram for the thermal ring opening of cyclobutene 4-pi system into butadiene. Let's unpack it step by step. 1. The reaction. Starting point, cyclobutene closed 4-membered ring. Reaction L, electrocyclic ring opening is produce 1,3-butadiene. Conditions, thermal no light. 2. The two possible transition states, TS. Disrotatory TS red, left, ends rotate in opposite directions. Symmetry element, sigma plane of symmetry. Conrotatory TS blue, right, ends rotate in the same direction. Symmetry element C2 axis of symmetry. 3. Orbital symmetry labels. On the left, we have the molecular orbital, MOS, of cyclobutene, sigma, pi, pi star, sigma star. On the right, we have the MOS of butene, psi1, psi2, psi3, psi4. The middle part applies symmetry labels. S equals symmetric with respect to the symmetry element, sigma or C2. A equals antisymmetric. 4. Rule of orbital crossing. Orbital of the same symmetry cannot cross energetically forbidden. Orbital of different symmetry can cross no problem. 5. The analysis. When symmetry labels are match across reactant is TS is product, the correlation forces an occupied bonding orbital pi to correlate with an unoccupied antibonding pi. This leads to a symmetry forbidden reaction. Great. This image is the Woodward-Hoffmann correlation diagram under photochemical conditions for the ring opening of cyclobutene 4-pi system. Let's carefully break it down. 1. Reaction overview 1. Molecule. Cyclobutene 1,3-butadiene. Conditions. Photochemical light excitation. Under light, one electron is promoted from a bonding pi orbital to the antibonding pi star orbital, is electronic changes. 2. Transition states. Two possible ways the terminal groups can rotate. Disrotatory TS sigma plane of symmetry, shown in red, left. Conrotatory TSC2 axis of symmetry, shown in blue, right. 3. Orbital symmetry labels. Each orbital, sigma pi pi asterisk, sigma asterisk, is given symmetric or A antisymmetric with respect to the chosen symmetry element. Left side. Symmetry under sigma plane for disrotatory. 4. Key photochemical difference. Because we are under photochemical excitation, the pi-pi star promotion occurs. So, instead of 2 electrons in pi, now we have 1 electron in pi, plus 1 electron in pi star. This changes how the orbital correlation works. 5. Pathway analysis. Disrotatory path, red, left. Correlations is smooth. Bonding orbital map onto bonding orbital of butadiene, psi1, psi2. An antibonding orbital map onto antibonding, psi3, psi4. No forbidden orbital crossing, is reaction symmetry allowed. Conrotatory path, blue, right. Correlation forces electrons into unfavorable crossing. Bonding is antibonding mismatch. This path is symmetry forbidden, disfavored. 6. Final rule for 4-pi system under photochemical conditions. Photochemical.
Disrotatory is allowed. Conrotatory is forbidden.
Perfect. This slide is showing the shortcut version of the Woodward-Hoffmann conservation of the orbital symmetry for electrocyclic reactions. Let's step by step. 1. Reaction being studied. System. Butadiene 4pi electrons undergoing ring closure, cyclobutene. We are checking which motion disrotatory or corrotatory is symmetry allowed. 2. Symmetry elements of the transition state. Disrotatory transition state has a sigma plane of symmetry red. Conrotatory transition has a C2 axis of symmetry blue. This matters because the molecular orbital symmetries must match under these symmetry elements for the reaction to proceed smoothly. 3. HOMO is the deciding factor. For the thermal reaction, we focus on the highest occupied molecular orbital of the starting material. In butadiene, the HUMO is psi2. The orbital drawing shows psi2 with its in-phase and out-phase lobes. 4. Orbital interactions. In a disrotatory closures, the terminal lobes of psi2 rotate in opposite directions. This rotation aligns the phases properly constructive overlap. New sigma bond forms allowed. In a conrotatory closures, the lobes rotate the same way. This causes destructive overlap, forbidden. This image explains cycloadditions and cycloreversión, specifically focusing on the Diels-Alder reaction. Cycloaddition definition: it is the union of two pi system with double bonds or triple. In this reaction, pi bonds are exchanged for new sigma bonds exchanged for new sigma bonds stronger and more stable. System. Example shown: A1, 3-DNA, conjugated DNA, 4 atoms react with a dienophile alkene, 2 atoms. This is called a 4+2 cycloaddition because 4 atoms from the alkene. A new 6-membered ring, cyclohexane, is formed. Diels-Alder reaction: it is the most famous 4+2 cycloaddition, involves 6 electrons, 4 from the DNA plus 2 from the alkene. Very useful for making cyclohexenes and calclohexanes in organic synthesis. This image explains the Fouquet frontier molecular orbitals. The reactant outcome can be predicted by looking at the HOMO highest occupied molecular orbital of one the other. Good overlap between these orbitals stabilizes the transition state and makes the reaction possible. DNA orbital left side. A conjugated DNA has pi electrons. These fill the lowest 2 molecular orbitals. Its HOMO has 1 bonding and 1 anit bonding interaction, shown in the middle orbital with 4 electrons. Its LUMO is the next unoccupied orbital above. Dienophile orbital right side. A simple alkene dienophile has 2 pi electrons. Its HUMO is the bonding pi orbital. Its LUMO is the antibonding pi orbital. Orbital interactions. Either the HOMO of the DNA overlaps with the LUMO of the dienophile, or the HOMO of the dienophile overlaps with the LUMO of the DNA. In this case, the energy GPS is similar, so either interaction is possible. The key factor is geometrical/spatial overlap of orbital. Energy diagram bottom rights. The stabilization of the transition state depends on greater than delta E energy difference between the HOMO and LUMO, greater than spatial overlap of orbitals. The closer in energy, the stronger the interaction, more stable transition, faster reaction. This image explains the 2 types of DLs. Alder reaction based on frontier molecular orbital interactions. Normal electron demand Diels-Alder. The most common case interaction. HOMO of the DNA overlaps with the LUMO of the dienophile, usually happens when the DNA is electron. Rich, the dienophile is electron. Poor example. Butadiene plus maleic anhydride dicyclohexene, derivative inversion electron demand. Diels-Alder, less common but important in bioorthogonal chemistry interaction. HOMO of the dienophile overlaps with the LUMO of the DNA, usually happens when the DNA is electron poor. The dienophile is electron-rich example. Tetrazene plus strained alkene. This image explains why the Diels-Alder reaction works using frontier molecular orbital theory. Orbitals of DNA left side. A conjugated DNA has 4 pi electrons. These electrons occupy its 2 lowest energy molecular orbitals. Its HOMO is shown in the middle level, partially bonding, partially antibonding. Its LUMO is the next orbital above. Orbitals of dienophile. A simple alkene, dienoplyle, has 2 pi electrons. Its HOMO is the bonding pi orbital. Its LUMO is the antibonding pi star orbital. The diagram shows the HOMO of the DNA overlapping with the LUMO of the dienophile. This is the thermal electron demand Diels-Alder reaction. The red dashed lines indicates favorable orbitals overlap between these frontier orbitals. Why bonding works? When these orbitals overlap, bonding interactions are created between the ends of the DNA and the dienophile. This stabilizes the transition state and allows the formation of a new 6-membered ring. The reaction works best when the HOMO-LUMO energy gap is small. The closer the orbitals are in energy, the more effective the overlap, leading to a faster and more favorable reaction. This image explains diastereoselectivity in the Diels-Alder reaction, specifically the endo and exo products. A substituted DNA reacts with a substituted dienophile A, 4+2 cycloaddition occurs, producing 2 possible stereoisomers. Exo product, minor. The substituent COOMe on the dienophile is oriented away from the Dien's pi system. Endo product, major. The substituent is oriented under or close to the DNA system. Let's see why endo is favored, endo rule. The endo transition state is stabilized by secondary orbital interactions. In the endo approach, the dienophile's electron withdrawing substituent CN overlap with the pi orbitals of the DNA. This extra stabilization lowers the transition state energy making. The endo product is major product. In exo orientation, these secondary overlaps are absent. This makes exo transition state is less stabilized. Here, the conjugated dyene has a HOMO shown with lobes of electron density. These orbitas are available for interaction during the cycloaddition. The dienophile has an electron withdrawing substituent. Its pi orbital extends not only over the CI double bond C, but also over the carbonyl group. This allows extra orbital overlap with the DNA. In the endo orientation, the carbonyl group of the dienophile can align beneath the DNA's pi system. This alignment allows the HOMO of the DNA to overlap with the LUMO of the dienophile's carbonyl substituent. These extra stabilizing interactions lower the transition state energy. In the exo approach, the carbonyl substituent points away from the DNA. These secondary overlaps cannot occur, so the exo pathway is less stabilized. Here we can see how substituents affect regioselectivity and reaction rates in the Diels-Alder reaction by influencing the HOMO-LUMO energy gap. Reaction rates dependence. The rate of a Diels-Alder reaction depends on how small the HOMO-LUMO energy gap is. Smaller gap leads to better orbital overlap, and that leads to faster reaction. Substituent effects on orbitals. Extra conjugation raises HOMO, lowers LUMO, leads to narrow the gap that leads to faster reactions. Electron withdrawing group lowers both HOMO and LUMO electron donating group. Raise both HOMO and LUMO. The C1 and C4 carbons are the reactive termini that interacts with the dienophile. Thus, substituent on the C1 carbon have largest effect on the reactivity and regioselectivity. Let's consider some examples of Diels-Alder reaction and how the substituents affect reactivity by changing the HOMO-LUMO gap. In the first, the maleic anhydride has electron withdrawing group, EUI equals O, which lower its LUMO, making it highly reactive towards the DNA's HOMO. The HOMO-LUMO gap is small, then the reaction is very fast and goes to completion at mild conditions. Second example is the ethylene has no substituents to lower its LUMO, so the HOMO-LUMO gap is large. Reaction is much slower and need harsh conditions. Yield is lower than the maleic anhydride case. This image is about region selectivity in Diels-Alder reactions, a paracyclic 4+2 cycloaddition. Concept of regioselectivity. The example involves a DNA with an OMe substituent electron donating and a dienophile aldehyde, electron withdrawing. 2 possible regiosomers can form. Major product, substituents align in such a way that electronic interaction are more stabilizing. Minor product, less favorable element, less electronic stabilization. The regioselectivity depends on polarization of the frontier molecular orbitals. Example of charge stabilization. Two possible resonance-like imaginary intermediates are drawn. First case major product. OMe donates electrons into the DNA system. The resulting positive charges next to OMe electron donating is stabilized. This leads to the more stable arrangement, major product. Second case, OMe ends up in a less stabilizing position. The positive charge is not stabilized as effectively. This leads to the minor product. Even though we use imaginary intermediates for prediction, the Diels-Alder mechanism is concerted. The intermediates is just a mental model for predicting regioselectivity. This image explains how to predict regioselective in Diels-Alder reaction by considering HOMO-LUMO interactions and imagining stabilizing charge distributions. The methoxy group stabilizes positivity charge, so the product where this interactions is maximized becomes the major product. This image explains the effect of Lewis acid and Diels-Alder reaction. Lewis acid effect. Lewis acid are among the earliest non-accelerator of organic reactions. They strongly enhance rate regioselectivity and endo or exo selectively in Diels-Alder reactions. Naphthalene plus maleic anhydride without Lewis acid. The half-life for the reaction is 2,400 hours, extremely slow. With AlCl3 Lewis acid, the half-life for the reaction is 2,400 hours, extremely slow, life drops to less than 1 minute, massive rate acceleration. Reason? AlCl3 coordinates to the carbonyl oxygen of maleic anhydride lowers the LUMO of the dienophile. Better orbital overlap with the DNA homofast reaction. Styrene plus methyl acrylate. Two possible regioisomers are formed, 1,4-adduct major preferred. 1.3 a adduct minor without additive ratio equals 80:20, with AlCl3 rate improves to 97:30 mush. Stronger regioselective because coordination of AlCl3 to the ester carbonyl polarizes the dienophile, making electronic interactions more selective. Cyclopentadiene plus methyl acrylate produces endo and exo stereoisomers without additive. Ratio equals 82:18, endo to exo, with AlCl3.OET2. Ratio becomes 99:1, almost exclusively endo product, because Lewis acid coordination makes the dienophile more electron deficient and strengthens secondary orbital interactions, which favor the endo pathway. Finally, we can state that Lewis acid increases the rate of endo/exo selectivity and regioselectivity. This slide explains why Lewis acid accelerate Diels-Alder reactions and hints at their role in selectivity. Why? Because the key reason is perturbation molecular orbital. The dienophile here is methyl acrylate. The Lewis acid, aluminum chloride, coordinates to the carbonyl oxygen. This generates a Lewis acid carbonyl oxygen. This generates a Lewis acid bicarbonyl complex. The oxygen donates its lone air to AlCl3. The carbonyl carbon becomes more electron deficiency effect on reactivity. The Lewis acid-bound dienophile is more reactive. It behaves more like an acylium ion in terms of electron distribution. This messens the LUMO of the dienophile is lowered in energy, so it overlaps better, the HOMO of the DNA. Resulu and faster Diels-Alder reaction. This slide digs deeper into why Lewis acid improve both rate and selectivity in Diels-Alder reactions using molecular orbital analysis. It shows frontier molecular orbital coefficients of a dienophile before and after Lewis acid coordination, and how this influences reactivity and selectivity. Key points in the image. Regioselectivity, left side red boxes. The lobe sizes on the terminal carbons of the dienophile differ. Without Lewis acid, the coefficients on C1 and C2 carbons are somewhat similar. Regioselectivity is weaker. With Lewis acid, the difference becomes larger. C1 carbon has a much bigger orbital coefficient than C2 carbon. The DNA preferentially reacts saying the carbon with the larger orbital coefficient leads to better regioselectivity. Middle blue arrow to lower LUMO equals faster rate. When the Lewis acid binds, the LUMO energy of the dienophile is lowered. Smaller HOMO-LUMO gap leads to faster orbital overlap, which results to faster reaction rate. Endo versus exo selectivity, right side on the dienophile carbonyl carbon. The lobe becomes larger when Lewis acid is attached. This larger orbital interacts more strongly with the pi system of DNA during the approach. Now, another key concept is Diels-Alder reactivity, the importance of the S-cis versus S-trans conformation of the DNA. S-cis versus S-trans. For a DNA to undergo to Diels-Alder reaction, the two double bonds must be aligned properly to overlap with the DNAphile. This requires the DNA to be in the Ursacsi-Sic conformation. Single bond between two double bonds is rotated so they are on the same side. In the S-cis trans conformation, the two pi bonds are too far apart. No cycloaddition possible. Simple 1,3 butadiene. Butadiene can freely adopt Si-cis and S-trans. The S-cis form reacts with malic anhydride, gives the expected product. This is the baseline rate relative rate equals 1,2, 3 minus dimethyl 1,3 butadiene. Here, the DNA can still totate into S-cis. Malic anhydride reacts faster, rate equals 4. Reason: extra methyl substituents stabilize the transition state via hyperconjugation and make the S-cis conformation slightly more favorable. 1-methyl cyclohexadiene. In this cyclic system, the DNA is locked in an S-trans-like conformation. Steric hindrance prevents adopting S-cis easily. This prevents good orbital overlap. Reaction is very slow. Cyclopentadiene. Cyclopentadiene is naturally locked in the S-cis conformation. As a result, it is extremely reactive toward malic anhydride. Relative rate equals 10 to the power of 3. Let us see why thermal 2+2 cycloadditions are forbidden using frontier molecular orbital analysis. Reaction considered: two alkenes combine to form a cyclobutene. At first glance it seems possible. 2 pi bond, 2 new sigma bonds. But orbital symmetry rules FMO analysis. Each alkenes has a HUMO and a LUMO. When you try to overlap the HOMO of one alkene with the LUMO of another in a supraphical way, this results in no net bonding. Destructive overlap. A thermal 2+2 Sic addition is symmetry forbidden if it proceeds superfacially on both alkenes. That's why simple alkenes don't undergo thermal 2+2 cycloadditions. However, under photochemical conditions, orbital symmetry changes, and the 2+2 cycloaddition becomes allowed. Now we can see how 2+2 cyclo-A additions can become allowed under an alternative orbital alignment, and why some special systems actually undergo them. If one alkene interacts superfacially and the other interacts enterofacially, then the overlap is constructive. This makes the reaction symmetry allowed. For normal alkenes, enterofacial interactions is geometrically difficult. Trying to bend one alkene to react enterofacially causes severe steric clashes between hydrogens. That's why typical alkene do not undergo thermal 2+2 cycloadditions. Superfacial plus superfacial equals forbidden. Superfacial plus enterofacial equals allowed by orbital symmetry. The another type of paracyclic reactions are known as sigmatropic reactions. A sigmatropic rearrangements is the migration of sigma bond across a pi system. The total number of sigma and pi bonds is conserved. These are classified as EM-N shifts, where M and N number of atoms separating the migrating sigma bond in the transition state. Here a hydrogen is migrating 1,3 shift. Does this happen thermally, supra or enterofacial? Let's know more about it. According to frontier molecular orbital theory, for thermal, a superfacial 1,3 shift is forbidden. Only enterofacial 1,3 shift would be allowed. But geometrically, this is almost impossible for small systems. Thus, 1.3 shifts are rare in thermal, but happen under photochemical condition. Consider this example, which shows a possible 1.3 shift where an alkyl group would migrate. According frontier molecular orbital theory, 1,3 shift is thermally forbidden because the thermal superfacial overlap is symmetrically forbidden. This is the general framework of a 3,3 rearrangement of 6 electrons in a cyclic transition state. FMO analysis reveals that it can be represented as 2 allyl fragments and gives 2 bonding interactions in the transition state. If the superfacial on both components, then it is thermally allowed. The transition state is usually chair-like, which makes stereochemistry predictable. Claisen rearrangement. 3,3-sigmatropic rearrangement involving allyl vinyl ethers. Converts an aryl or a chiral-allyl ether into a gamma, delta unsaturated carbonyl compound. Driving force CAN gives the formation of a strong C double bond O. The pi bond of carbonyl group is more stable than pi bond of alkene dot, so delta G greater than 0. Thermodynamically favorable reaction. Oxy-Cope rearrangement. The Cope rearrangement is a 3,3-sigmatropic rearrangement. When a hydroxyl group is present, it becomes an oxy-Cope rearrangement. In neutral cases, the hydroxyl group does not strongly affect the reaction, but in anionic cases, deprotonation massively accelerates the reaction rate. This slide is about the Dewar-Zimmermann theory, which provides another way to rationalize paracyclic reactions using aromatic transition. State Dewar-Zimmermann, aromatic transition state. The idea is that paracyclic reactions proceed through aromatic transition state if they are thermally allowed, and through anti-aromatic transition state if they are photochemically allowed. Procedure: choose basis set of orbitals. For carbon atom, 2p orbitals. For hydrogen, 1s orbital. Assign phases. Put plus and minus phases arbitrary on orbitals. Connect orbitals that interact in the transition state. Count the number of phases inversions. Identify topology. If there are any odd number of phases, inversions leads to Möbius topology. If there are any even number of phases, inversion leads to Huckel topology. Assign aromaticity of the transition state. If the transition state is aromatic, then the reaction is thermally allowed. Assign phases. Put plus and minus phases arbitrary on orbitals. Connect orbitals that interact in the transition state. Count the number of phases inversions. Identify topology. If there are any odd number of phases, inversions leads to Möbius topology. If there are any even number of phases, inversion leads to Huckel topology. Assign aromaticity of the transition state. If the transition state is aromatic, then the reaction is thermally allowed. Thank you for watching. Please like, share, and subscribe. Support me for next videos.